Thank you, Ian. Do you see my slides?
Yes.
Okay, good. So yeah, in the presentation I have make the title shortened. So now it is machine learning based characterization of software performance regression. This is basically this work is mainly done by my student Vladislavs, and then we had to fix some of the issues here. Shubal and me were involved here and fixed some of the issues. And Bolbokar was mostly interested about this work, and later Bosch also was with us to see the progress. Uh, so, what is the problem? The problem is, for example, in the software development, usually we have a master repository that contains the software that the most stable software, and then different developer basically they try to upgrade the system in order to fix the software bugs or add some functionalities into the software or for some other reasons. So the developer has a working copy of the software which may be different from the main repository. So what happens is that once the developer upgrades his system in the developer copy, then there there may, due to this upgrade, the developer may introduce performance regressions, and by performance regression I mean that there may be unexpected loss of performance. I mean, there can be expected performance loss. For example, in order to introduce new functionalities which may take more computational resources, that can be fine. But there can be something unexpected where the upgraded software in the developer copy uh, may take more time or more computational resources such as memory. Uh, Even if the same workload is provided to the software. So this can happen, and if the developer commits his code to the repository, then the main repository will now contain performance regressions. The problem is not good for many systems, for example, web services or cloud softwares or other time critical systems. So this kind of performance regression is not good. So what is done today is in order to detect this kind of performance regressions, performance tests are performed. And the problem with these performance tests is it takes a lot of time to run the performance tests and to detect if there is really any performance regression or not. Then we were thinking, I mean, can we use some kind of machine learning approach to detect such performance regression? The idea is that even if this machine learning approach, it may take some time in the offline to learn the model. In the online, probably it can predict something very quickly. There are other benefits. So this was a preliminary idea of whether we can, if we can develop such kind of system to detect performance regressions. So I'm not going to the details of a general neural network, but the idea is that the general neural network usually takes numerical inputs. However, in our case, we have source code, which are text program instructions. So the high level architecture of our system should be, I mean, what we expect is that we have pairs of source code here. One in the main repository, that means the more stable version of the code, and the other one is the developer copy who has made some changes in his copy. Then once we receive these two pairs of code, we do some kind of cleaning of these two pairs of code. By cleaning, we mean we remove all the unnecessary information in the source code that we know are not required to detect performance regressions. And since deep learning networks usually work on numerical input, somehow we need to represent this source code by using some kind of vectorization method. the idea of this vectorization method is that it tries to learn a numerical representation of the code and represent the code by some kind of vectors, some vectors of real numbers. Then we give these two vectorized representations to some kind of neural network architecture that we have developed here. And this neural network architecture then compares these two pieces of code, and then it predicts if there is any kind of a performance regression or not. So that's the high level architecture. So in order to generate this model and to test also this model, so we have worked with the source code of the Git version control systems. So the main reason to use the source code of Git is that we have the performance regression labeling of the Git software that we have obtained from one of our colleagues who developed the price tool. It is also based on some kind of machine learning architecture, but the price tool basically what they give is they give the characteristics of the code. But in our case, we did not give the characteristics of the code as input. Rather, we asked the deep learning structure to learn those characteristics to detect performance regression. That's the difference between our approach. Down almost 9,000 commits from GitHub, and for all those commits, this performance regression labeling are already done by the price tool. So we have this labeling. And in the cleaning phase, what we did is, for example, when we download the commits there, along with source code, there are other kinds of files as well, which we discarded. We don't need those files. We only keep all the C files and copy it to the text files. And in the pre-processing phase, what we did is that we remove all the comments and punctuation marks, brackets, etc. And also we remove literals from. Then we replace some of the words that are very less frequent, and we know that this kind of words will not contribute to performance regression. So we replace those infrequent words by some special tokens. And then we use some kind of shallow neural network to learn the embedding of the tokens of the source code. So this embedding will give us the vector representation of the code. And to do that, so nowadays there are different kinds of embedding techniques for source code. But in this preliminary work, what we did is we use the most simplest one, word to vec, which is a kind of word embedding technique used for natural language processing, which has been developed by Google engineers in 2013. And the good thing of this word to vec is that it is very fast because it is based upon the shallow neural network, and it can capture the content of words in a document. That means it learns the distribution of a token based on what are the other tokens surrounding it. In this way, it can learn syntactic and semantic similarity. So, for example, in the source code, the token for if and while we get similar kind of vectorized representations because both if and while they have conditional instructions. So in this way, we can ensure that they have some kind of semantic similarity in the learned vector representations. And this tool is already available in the Google code base, which is based upon Keras and Gensim. So what we get is, for example, in the left, this is the source code. After cleaning, you see it does not have any kind of delimiters or punctuation marks that we have removed. And in the right, we get this kind of vectorized representation of the source code. Then we have come up with a deep learning architecture like this, which is a kind of Siamese neural network. We have generated 120 models, and out of these 120 models, we see this is the model that performs better than the others. And this CMC neural network, it has, you see, there are two kinds of two inputs basically. In the left, we take the old commit. Old commit means the commit. Here, a commit means a version of the software. So in the left, we take the stable copy of the software that is in the main repository, and in the new commit, that means the developer version of the software. And basically, they are not software, but they are the how is it called, one hot vector, which is built based on the what should I say, based on the position of the tokens in the dictionary. Then you see this, there is a common embedding layer, which is the word-to-vec shallow neural network. And this 100D means this our vectors is 100 dimensions, because we need to restrict the size of the vector due to memory limitations. So and in both sides we have this common embedding layer, and this common embedding layer basically learns the vectorized representation of the source code. Then we give this source code to this common LSTM, which is a kind of recurrent neural networks, and this layer has 50 units. So the idea of this LSTM is that it will learn the sequence of tokens. That means it will learn the context of the source code, and then we use the tangent activation function, and from after learning both the old vectorized representation and their context of the old new repository, some kind of features. For example, one of the features is the cosine distance between the vectors, and there are other features that we have extracted, and we give these features to a dense layer, which is a fully connected layer, which contains, the first dense layer contains 128 nodes. Also allows the tangent activation function. In the hidden layer, we have 50 units, which uses ReLU activation function. And the final layer, basically, it has only one unit because classification saying that either I have performance regression or not. So that's why in the final dense layer, it has only one unit, and we use sigmoid function here to predict the performance regression. So that's the architecture that we have come up with. Then for the experimental evaluation, out of all the commits, we have 9,150 commit pairs that say it does not have no regressions, and 401 pairs which has regressions. So what we evaluated is that, I mean, basically we try to do some kind of binary classification saying regression or no regression whenever two commit pairs are given to this kind of neural network architectures. And you see already this is a very imbalanced data set which influences our outcome. Because 401 is, I mean, very imbalanced with respect to 9,150. Nevertheless, we wanted to see how it behaves. So what we get is that we get a maximum accuracy of 75%, minimum accuracy of 19%, and average accuracy of 37% for detecting performance regressions. And then this result is based upon fourfold cross validations. Then we also measured hit rate and dismiss rate. And hit rate means that, okay, it is the ratio of the number of commit pairs that says performance regression exists with respect to the total number of commit pairs that has performance regressions. And dismiss rate is the other way around. So it is the ratio of the number of commit pairs that we have said to have performance, no performance regression, divided by this number of commit pairs that really have no performance regressions. And from this layer, you see, from this result, you see that this dismiss rate is very high, which means that if the commit pair does not have performance regression, then it can accurately detect it. But on the other hand, if you look into the hit rate, you see that the hit rate is very low, which means that in case if there is performance regression, so sometimes it can detect it on an average 37% times, but not all the times. And from the graph, you see, I mean, it says some kind of how is it called, inconsistencies in the model we have found because of the imbalanced data sets, because you see the difference between the error in the training and test sets. This says that, I mean, we still can improve the model if we provide balanced data sets. So, so this was the preliminary study. I mean, we did not spend, we could not spend too much time on further developing these models and these algorithms. Nevertheless, the estimated accuracy that we have found, the average accuracy 39 to 42%, is not so bad when we compare other machine learning based softwares. And other machine learning based software, basically they never try to learn automatically the code features. In our case, we try to learn these kind of features. So that's the main difference, which we believe it can be improved a lot. And one of the source of imprecision is the word embedding techniques, which is mainly good for natural languages, but it is not good for understanding source codes. So what can be done to upgrade the system is that we are planning to use much sophisticated source code representation techniques. For example, code embedding techniques or flow embedding technique. There are these two kind of techniques now exist, and we even believe that even though code embedding or flow embedding techniques are there, this kind of embedding techniques can be improved a lot depending on what kind of feature we want to extract. And this architecture that we have come, we use LSTM, but nowadays there are other sophisticated deep learning architectures such as graph neural networks or transformers. We have not tried those kind of architectures, but we believe that if we replace this architecture, then it will be able to better predict the performance regressions. And then in our group, we are thinking about some kind of future roadmap. What can be done based on analyzing source code artifacts using deep learning techniques. So it is a relatively new research area, a new and emerging research area, I should say. And lots of works are going on. And still it is a very early stage of this kind of research. So some challenges are, for example, how do we understand the statistical or neural language models? The better we can understand these models, the better we can infer the properties of this kind of properties of these artifacts, source code artifacts. And some of the uses that we can use deep learning is, for example, API migrations, where the code is developed in one language, but at some point the management wants it to shift it to another source code. Then for this kind of API migration, this kind of statistical language model is very good. And there are other uses, for example, code clone or code smell detection that basically says that basically talks about the code quality. And for example, we can nowadays this kind of neural networks are used to detect software bugs as well, software security analysis, also code completion or defect analysis. This kind of, I mean, these are all the are few of the things that in which we can use this kind of deep learning architectures. So I think there in this area we can do a lot of things if we get support, of course. So that's all from me.